Matrices, they have one of the most applications of math in the business world. Many uses in real life. One basic application you could see that would just kind of help you understand how businesses, how they might be really applicable for businesses, is just this simple looking at packs of noodles sold and packs of rice sold. It says one application would be to use matrices to represent a large amount of data in a concise manner so that we can process the data in various ways more conveniently. For example, the sales of different types of pre-packed foods from 3 stalls during a given period of time could be shown in the form of a table here, where we're looking at how many packs of sold are in week 1. So you can see for stall A, packs of noodles would be 36 sold. Stall B is 21. Packs of noodles sold in stall C would be 43. So it appears in week 1 that stall C as the best sales representative, or maybe they had the most traffic in that area to sell the noodles, and then the packs of rice sold. Let's see how we could translate this information into a matrix. A matrix is just an array of number. You use these brackets to represent the elements in the matrix. And we would obviously take the numbers 36, 21, 43. Now this would represent row 1. In matrices, we use terminology like rows and columns. So it's important that you recognize what each piece is called. Then in row 2, we would have 27, 56, and 35. So this would correlate to row 2. And then what do you guys think the up and down pieces would be called? Columns. So this would represent column 1, column 1, column 2, and that would be column 3. Now, why is it important that you understand those terms? Different elements are labeled by where they fit in the matrix. For example, if I'm looking for the element A12, I'm looking for which number corresponds to row 1, column 2. So A12 represents the element in row 1, column 2. So if I'm looking for that specific value, what would that represent? Nate?
Oh, I was just going to ask, is there any way to tell the 1 and 2 apart? Like, what if there was a 12th row? Would you be looking at the first one or the 12th one?
So if there was a 12th row, then there would be kind of 2 numbers. So you would be like 12, 1. Or they may, to be honest, in college algebra, we don't really work with matrices that high, but I'm sure that if you had a 12th row, they would probably put parentheses around the first number, which represents the row, and then the second number, which represents the column. But that is something really important to be aware of, that the row 1, that piece represents the first number, and the second piece represents the column, the corresponding column. So if I was looking at row 1, column 2, which element would be represented in that value? 21. So that would be just kind of how I label each element, and that's how you will see them labeled in this matrix chapter. And then also, matrices are given to you by their dimensions. So the dimensions of this matrix, or of any matrix, is labeled its rows by columns. So for example, the dimensions of this matrix would be a 2 by 3, representing that there's 2 rows in this matrix and 3 columns. Rows by columns. The way that I always remember that, has anybody ever drank the pop RC Cola? RC Cola. It's a kind of like a Pepsi. It's an off-brand. I think they used to sell it at Aldi. And when I was younger, we didn't have a lot of money, so if my mom bought pop, it was like RC Cola. And so we would now they're just as expensive. I don't know if it's more popular now, but we'd always have RC Cola, and it was just a type of cola. And for whatever reason, when I think about matrices, I remember the word RC Cola to help me remember just how matrices are labeled, rows by columns. Okay, now let's see, how could this be helpful in the business world? Well, if we're looking at a week 2, And we have packs of noodles sold in stall A was now 40, stall B was 31, stall C was 40. Packs of rice sold were in stall A 20, stall B 40, and stall C 30. We could combine weeks 1 and 2 and see what is the total sales for both weeks. And that's really, a lot of this can be done on the computer as well. And so just businesses can access information quickly and efficiently and see maybe which stall is better, and then analyze why that stall would be better at selling. Is it a better salesperson? Is it just more traffic in the area? Just really what is causing that business to sell better? And they analyze this and they make decisions based off of that data. So we can see if we take that first matrix, and we can even see how simple matrix operations are performed. So if I take that first matrix of 36, 21, 43, and 27, 56, 35, and I add this to the week 2 sales, then so this would represent week 1 sales, and add this to week 2. Well, then we can take this information and organize it into a 2x3 matrix as well. So we would have a row of 40, 31, and 40, 20, 40, and 30. And now you guys can probably already predict how you would perform matrix addition. How do you think we would add 2 matrices? Each spot, each corresponding element. So I would add like 36 plus 40, and that would give me a 76. Add 21 plus 31, and that would give me a 52. Add 43 plus 40, and that would give me an 83. 27 and 20 would give me a 47. 56 and 40 would give me a 96. And 35 and 30 would give me a 65. And this would tell us our week sales from 1 and 2. From 1 and 2. Now, one thing that's illustrated in this basic example is matrix addition. Matrix addition or subtraction has to be performed on matrices with the same dimensions. And that's a really important thing that we should even like maybe bold in. I'll go ahead and put it in red. And you'll see that on the next page. But matrix addition or subtraction must be done, or only can be done, on matrices with the same dimensions. So for example, this 2x3 matrix, if I add that with a 2x3 matrix, I know that it's going to create a 2x3 matrix. Is that your question, David?
No. Oh, no. So, like, can you, will there ever be negatives?
Yeah.
Where, like,
yeah, for sure. Yeah. I mean, oh, you're saying for this particular example? Would
yeah,
there...
Could there be, like, a negative 76?
You could... For stores, if it costs so much to rent the place and to produce the product, and then they didn't sell, like if you're talking about money, profit, there could be negative because we're in the hole. We didn't sell what we needed to make up even the rental of the place. So that's why you could have subtraction, just different scenarios. And then real quick, guys, before you flip the page, let's just make sure we know with this new matrix that we found, what does the number 96 represent? Like, we just want to see how would the stores analyze the data. So they have this new matrix. Maybe their computer did the operation. It added week 1 plus week 2 of what? To week 2. But if we analyze that number, what would it represent? Stall B, packs of rice sold, right? So we just want to make sure we can see how to pick out that element and what it represents in a real life scenario. So what does the number 96 represent? The total sales for packs of rice. That's a weird packs of rice sold in stall B for weeks 1 and 2. Okay, that was a real basic matrix or real life example just to kind of see how matrices are applicable. The next page we're just going to see, now that you know how, maybe a little way of how they're used, let's see that if you know how to, one, label dimensions, and then perform addition, subtraction, and basic scalar multiplication with matrices. So again, a matrix is just really an array of numbers, and there are many applications of matrices. Let's do this first example together. What would be the dimensions of this matrix here? Good, it's a 1 row by 3 columns. So 1 row by 3 columns. Therefore, what would be the element A12? What corresponds to row 1, column 2? The number 8, good. Why don't you go ahead and try the next 2 with your partner? All right, let's hear from a few of you. Alex, what'd you get for the dimensions of this matrix? Yeah, second one. 2 by 2, excellent. What was the element that corresponded to row 2, column 2? Excellent. Nice. Next one, let's see. Katie Barman, what'd you guys get for the dimensions of this one? Excellent. 3 rows by 2 columns. And what'd you guys get for the element that correlated to row 3, column 1? Excellent. Give me a thumbs up if we got that as groups. Yeah? All right, we're ready to move on. Addition and subtraction, again, are done element by element. So can we add this matrix together? This is a 2 by 3, and we're adding it to a 2 by 3. Can this be performed? Yep. What would the resulting matrix become? 2 by 3. So if I add -1 plus 4, add the corresponding elements, I would get in row 1, column 1, the answer would be 3. Add 2 plus 10, and I would get 12. 5 plus 2, and I get 7. 8 plus -1, and I get 7. 9 plus 3, and I get 12. 10 plus 8, and I would obtain 18. So there would be my answer. Let's take a look at the next example. Subtraction is done element by element. This matrix currently is a 2 by 2. Well, it is a 2 by 2, not currently, it is. And then this matrix here is a 2 by 1, 2 rows, 1 column. Is it possible to subtract these two? No, because they're not the same dimensions. And you can't add any numbers to a matrix. Many people want to just add zeros, but it's not the way matrices work. Matrices come from real life data, and so in this case, we just say, hey, we cannot subtract. You're not looking at the same pieces of data like rice is sold or noodles sold. Okay, looking at the next 2 examples, solve for x and y. If you're adding 2 matrices and you come together to get a result, you just need to know that you added the corresponding elements. So for example, -1 plus y we know is equal to what value? 9. X plus 2 is equal to what value? 10. And we could confirm that. We don't have to write this, but is it true that 3 plus 4 would have to equal 7? Yeah, so I don't need to write it. And then 4 plus 9 would have to equal 13. Now, what would I do, obviously, to solve for x and y? Just solve the equation. So what is y equal to? 10, good. And then what is x equal to? 8, excellent. Don't you guys love matrices? I feel like they're just so nice. They're so simple. It's just a lot of numbers kind of in one equation. Okay, if we're looking for 2 times x minus a equals b, and we're solving for what matrix did you multiply by 2 in order to get this result, we would go ahead and fill in 2 times x minus, we can fill in matrix A, which is 2, 3, -5, and 1, equals matrix B, so we have 4, 1, -1, and 3. And our operations, our rules, they work in the same way as normal equations. So what would we do first here to solve for matrix X? Yeah, add that other matrix, add this matrix to the other side. So we could go ahead and add that. So we would have 2x is equal to 4, 1, -1, 3 plus that other matrix. So plus 2, 3, -5, and 1. And now we can go ahead and add those corresponding pieces. So 4 plus 2 is 6. Negative 1 plus 3 is 2. 1 plus negative 5 is negative 4. And 3 plus 1 is equal to 4. And then how do you think we'd solve for matrix X? Divide by 2, or you could think multiply by 1/2. It's a scalar, which we're going to look at in the next example. But we would have X is equal to, what do you think we're going to do with the 1/2? Distribute it in. That's scalar multiplication, just multiplying a matrix by a number. So half of 6 comes out to be 3, half of 2 comes out to be 1, half of negative 4 is negative 2, and half of 4 is 2. So there would be our answer. Now, one thing to recognize is that scalar multiplication can be performed on any matrix. What is scalar multiplication? It's just multiplying each element inside the matrix by a constant. So if you see one little number on the outside, we know that we can distribute it in. In this case, it would become 4, 12, negative 2, and 6. However, as you are looking at real matrix multiplication, multiplying two matrices together, it's not quite that simple. So let's go ahead and let's take a look at the next page, which is matrix multiplication. It says matrix multiplication is very different than other matrix operations. The process does not multiply element by element, as you can see in the following example. So notice, this is bad. This is a not equal. If I'm looking at the dimensions of these matrices, essentially a 2 by 1 multiplied by a 2 by 1 does not create a 2 by 1. Matrix multiplication, it's special, and we're going to see how it works just by looking at brands of shoes. It says the large department stores and shoe companies carry out market research to gather information about brand switching for top-selling products. Suppose that the results of matrix research in brand switching by customers of one large shoe store are shown in the following matrix. So here's what's happening here. We have a current brand, and these are people who currently have Nike, Reebok, or Fila. And how many percent of them switched brands? So if I'm looking at how many people currently have Nike but then maintained Nike, it was only 40%. How many people have Nike but switched to Reebok was 40%. And then how many people currently own Nike but then bought Fila the next year was 20%. So that's how the matrix works. And I just really explained what was shown in here. But it says, for example, the entry in the second row and third column is 30%. So second row, third column. This means that 30% of the people who own Reebok expect to buy, am I saying it right, Fila? Fila? Is it Fila? Fila next year. I have a pair of those. I just wasn't sure what they were called. And it says, what percentage of people who now own Nike expect to buy Reebok next? So why don't you take a second, read through this, make sure you know how this matrix works because we are going to be working with it, and answer these questions A through C with your partner. Just how it works. Check your answers. A was 40%, B was 50%, C was Fila because 70% will buy the same brand. Okay, now assume that the buyers buy a new pair of shoes every year, and suppose that this year 700 people bought Nike, 500 people bought Reebok, and 400 people bought Fila. How many people expect to buy Nike next year? So I'm going to kind of bring it back so I can revisit that matrix. What would I do to determine how many people expect to buy Nike next year? Well, if currently 700 people bought Nike, how many people are going to, or how can I figure out how many people will buy Nike next year? Yep, multiply that by 0.4. And now I want to see the total people that will buy Nike. So now 500 people bought Reebok. So how many out of that 500 people will switch to Nike for the next year? 20%. So I'm going to add that to 500 times 0.2. And it says 400 people bought Fila currently. So how many people out of that Fila category are going to switch to Nike for the next year? Only 10%. So I'm going to take 400 and multiply it by 0.10, and then we can find our total. And so how many people total out of that value would buy Nike? Put that in on your calculator. It comes out to be 420. Okay, with your partner, do letter B. Okay, so go ahead and check your answers. It should be 610. Now, below is a way to answer the question above using a new matrix operation. A one-row matrix for this year's numbers is written before the brand switching matrix. So notice it says 700 people currently own Nike, 500 Reebok, and 400 own Fila. And we're looking at multiplying this by those percentages to determine how many people are going to buy Nike, Reebok, or Fila next year. So it says complete the computations below for the number of people who expect to buy Fila next year. So currently there's 400 people who own Fila. And it says the number of people expecting to buy, but there's 700 who currently own Nike, 500 who currently own Reebok, and 400 who currently own Fila. It says find the number of people expecting to buy Fila next year. So what would we multiply 700 by to determine the Fila? 0.2 plus 500 times 0.3 plus 400 times 0.7. We can figure that out on our calculator, and that would come out to be 570 people. Now, this is actually helping us understand matrix multiplication. To which column of the brand switching matrix do the numbers in the blanks that you just filled out, to which column do they respond? Column 3. Which column of the brand switching matrix can you combine with the one-row matrix, that's this one here, to get the number of people who expect to buy Reebok next year? Column 2, good. Because Reebok is in column 2. So explain how the row and the columns are combined. Well, the row 1, if I'm looking for example, if I'm looking for which number, 570, would, well, that's a little bit hard too. We need to come back to this question after you guys see the matrix multiplication. But really, it's the rows line up with the columns. You're multiplying the row numbers by the line that's vertical in the columns. So you guys can see that we did 700 times 0.2, 500 times 0.3, 400 times 0.7. So that row 1 lined up with column 3, and that's what allowed you to add the total amount of people who would buy Fila. So I think of lining the row up with its matching column. But looking here, it says this method of combining a one-row matrix with the columns of the brand switching matrix is called matrix multiplication. The result can be written as another one-row matrix. For example, using the computations you've already done up at the top, list the entries of the one-row matrix on the right below. So if we took this row 1 by 3-column matrix and multiplied this 3-row matrix by 3 columns, we're going to get a result of a 1 by 3 matrix. If we look at how many buyers this year currently bought Nike, Reebok, or Fila, and we multiply it by the brand switching matrix to see what they will switch to, we can get the projected buyers for next year for each brand. So for example, how many projected buyers are going to buy Nike next year? Look at the top of your page. 420. How many projected buyers for Reebok? 620. Was it 620? 610? And how many for Fila? 570. Now you just did matrix multiplication. That's how it's used in a real world business type setting. But a few things I want you to analyze or to look at. Notice that the dimensions are not the same. We multiplied a 1 by 3 by a 3 by 3, and we obtained a 1 by 3 matrix. What has to happen in order for you to be able to multiply matrices? Which two numbers do you think have to match? So the columns have to match up with the rows of the second matrix, because we're essentially taking that row and lining it up with the columns. So we need to make sure that those two middle numbers match. So we can go ahead and make a note here, but the middle must match in order for matrix multiplication to occur. The matrix multiplication. Okay, so I just have thrown just a few additional examples just for us to really drive this home. Taking a look at this matrix multiplication, we have a 2 by 2 matrix multiplied by a 2 by 2. Is it possible to perform the matrix multiplication? Do the middle two match? Yes, and in fact, the resulting matrix is going to be a 2 by 2. Those outside dimensions are going to show you what the resulting matrix will be. What happened? Oh, did you? I'm sorry, I switched out the notes. Half of them don't have it? Oh, I'm sorry, guys. So do I even have the video still recording? I don't even know. Yeah, I do. Know that our result is going to be a 2 by 2. And we're going to see how do we obtain the element in each part of the matrix. So first let's label what each element, what its position is called. So if I'm looking at finding the element that will occur in row 1, column 1, let's start there. How do we obtain the element that will occur in row 1, column 1? Well, if I'm looking at these two matrices, I'm going to multiply row 1 by the elements in column 1, and then I'm going to add their products. So let's rewrite the matrix just because it's the first example, the first time we're doing this, just to see how this occurs. And if I'm looking for what happens in row 1, column 1, I take row 1 of the first matrix, multiply it by the corresponding elements in column 1 of the second matrix, and the sum of the products will end up in that position. So I would take -4 times -2, -4 times -2, and I'm going to add that to what? 0 times 0, which is 0. So I can see that the element in that position is going to be a +8. Now, why are we adding those numbers? You saw it with the switching brand matrix. You have to add those products to determine the total. Okay, let's take a look at what would we do for row 1, column 2. Well, looking at this same problem, we're going to take row 1, and what do you think we're going to multiply it by? Column 2. So let's rewrite it just because now we're finding row 1, column 2. Just because this is the first example, I want to do this step by step. So rewrite this problem. I'll erase that. Rewrite -4, 0, 1, 3 multiplied by -2, 4, 0, 1. And if we're finding the element in row 1, column 2, we're going to take row 1. We're going to multiply it by the corresponding elements in column 2. And we will obtain the element that will exist in row 1, column 2. So we're going to multiply -4 times 4 and add that to what? 0 times 1, which is 0. And what will that second element be? -16. So I can go ahead and I could bring down that 8 just because that was already there. Okay, how many more elements do we have to find? 2 more. So the next one would be row 2, column 1. So to find row 2, column 1 answer, I'm just going to rewrite the problem. I know this is a lot of writing, and you won't do this for every problem. This is just because it's the first one we're doing. I really want to drive home the process. But if we're looking for the element in row 2, column 1, we're going to take row 2, which is 1, 3, and multiply it by the elements in which column? Column 1. So we would have 1 times -2, which is -2, plus 3 times 0, which will become 0. So what would that element be? -2. So we're almost done. We have a result of 8, -16 in the first row, and then a -2 in the third row. And then last but not least, we need to find the element that would exist in row 2, column 2. So I'm going to rewrite the problem just for this example. And I'm going to take row 2 of the first matrix and multiply it by the corresponding elements of column 2 of the second matrix. So I multiply this by this, and I get an answer 1 times 4 plus 3 times 1. And what is my final element? What does that answer come out to be? 7. So my resulting matrix is 8, -16, -2, and 7. Okay, we're going to practice more with this tomorrow. Is tomorrow Thursday? Yeah, Thursday, tomorrow. But I just want to see what dimension should occur here. So if you're taking a 2 by 2 matrix and you're multiplying by a 2 by, how many columns are there? 4, what resulting matrix should you get? 2 by 4, because the middle dimensions match and they essentially cancel. And so your results are the outside dimensions, 2 by 4. So right away, you could, and this is probably where we'll start on Thursday, but you could set up 2 rows, 4 columns, and you know that you're going to have that amount of elements to find for your product. But we'll go ahead and stop there.